Hi, I'm Cheryl Miller and I'm presenting my final project for Georgia Tech's Big Data for Healthcare. In this project, I evaluate big data technology use for the purpose of analyzing health-related data. I will be covering the following topics listed on this slide. Spark for Healthcare has great potential for the greater good. However, it requires a great deal of trust on the part of the healthcare community and the public at large. To that end, it is critical that analysis and the data it's based on be reliable. Spark is new and complex, so requires expertise and easy interfaces, or systems may have reliability issues. Here, we implement a simplified emulation of Henry et al.'s TrueScore paper. They developed a measure for identifying patients at risk of septic shock, a leading cause of death in ICU patients. Sepsis can lead to septic shock, but is treatable if detected early and aggressively. Henry used MIMIC2 data to build a Cox proportional hazards model using a continuous input window. Ours simplifies that to a point-in-time classification model where we use many of the same input features from the MIMIC3 data. The MIMIC3 data is nowhere near the size of most big data projects, but it did prove large enough for us to struggle with scalability issues. The cohort was based on adult ICU patients over the age of 15. We first built out a Postgres database to become familiar with the structure and data related to sepsis, particularly those metrics and ICD-9 codes referred to in Henry's paper and supplemental materials. The critical time-sensitive data was available in event files. The chart events file alone was over 27 gigabytes in size and over 285 million records. We created control files defining sepsis-related item and diagnosis codes, generalizing these into appropriate feature label groupings. We filtered the larger data set to a more manageable size based on patient cohort and the sepsis items. We ran the filtering task on an AWS EMR 4.4 cluster. The cluster contained the latest Hadoop and Spark releases, allowing us to use new Spark features such as data frames, windowing functions, and ML pipelines. Since our focus was Spark suitability for healthcare, we simply selected random forest classifier for modeling due to its robustness to overfitting. Spark's ML pipeline API is easy to use while still allowing control over tuning parameters. The main pipeline implemented is outlined in this slide. We did find the data quality and features available from the MIMIC3 data had a big impact on the prediction performance, so we wanted to highlight them here. Looking into the future is not valid when developing predictive models. Using the ICD-9 codes as features is a form of that, since they were assigned after the fact for billing purposes, and no time criteria are associated with them. Existence of infection proved to be important, though, and had a big impact on prediction performance. We kept these ICD-9 codes as features per the belief that infection would be a known element during ICU treatment. In this case, sepsis is dependent on infection and septic shock on sepsis. The accuracy measures reflect this between the first table, where all features were used, and the second, which excluded sepsis, infection, and severe sepsis. In the latter case, precision and F1 scores dropped dramatically. The precision recall curves on the right also reflect this as we go from all features to excluding just sepsis, and finally excluding sepsis and infection and severe sepsis. This highlights the need for clean, consistent, and time-based recordings of health metrics. Because we ran out of time dealing with Spark reliability issues, we were not able to perform the scalability tests we wanted. Instead, we have listed some subjective lessons learned from the viewpoint of a Spark novice, key of which are Spark is still buggy. As of April 23, 2016, there were over 1,400 outstanding major issues logged. Spark tends to throw exceptions frequently, killing our job in particular if your data frame processing gets overly large or complex. While the new data frames are inherently parallelized, some key features like fill forward and fill backwards are missing. Memory tuning is not a trivial task, and writing code for parallelism requires a new mindset. While we struggle greatly to learn and implement this project in Spark, we still have high hopes for this platform. The Spark developers are on the right track as far as ease of use with the new data frames, windowing, and ML pipeline features. But focus needs to be placed on working out the bugs and making it easier to transition to true parallelism. Focus also needs to be on making memory tuning easier, so you don't need to be a Java, Spark, or Hadoop memory expert in order to gain parallel processing advantages. Finally, in order for automation and analytics to be successful, reliable, and trusted, the healthcare data used as input needs to become better, standardized, and of higher quality. As the old adage goes, garbage in, garbage out. The garbage in can come from extremely dirty and inconsistent data, from bugs due to inexperienced developers using Spark, or from Spark bugs themselves. An easy-to-use interface will go a long way to aid inexperienced developers, but the Spark platform itself must become more stable and reliable as well.